Building a backend system that can process 1 million concurrent users flawlessly is, at its core, a complex mathematical challenge. The specification dictates strict operational limits. The system must maintain 4 nines of uptime, that is 99.99% availability, and enforce a hard ceiling of 200 milliseconds for every response. In a traditional monolithic architecture, all application logic, routing, and database functions execute on a single centralized server instance. When a sudden traffic spike hits 100,000 requests per second, this centralized model rapidly exhausts its connection pool, creating a complete system lockup. The failure stems from synchronous processing. As the server waits to finish each task, memory constraints limit execution. When the incoming load exceeds the physical hardware capacity, the server drops connections entirely. To survive scale at this magnitude, upgrading the server hardware is insufficient. The system's internal components must be explicitly decoupled and distributed across multiple independent nodes. Moving to a cloud-native architecture is driven entirely by the physical limitations of centralized computing. The first geographic obstacle in our specification is serving a globally distributed user base without breaching that 200 millisecond latency limit. This map illustrates network latency. Routing global requests to a single data center means distance dictates time, causing unacceptable delays. By deploying a CDN, we intercept requests at regional edge nodes near the origin, drastically cutting travel time. The CDN caches static assets locally. This immediately filters out a massive percentage of total traffic before it ever makes contact with the backend infrastructure. The traffic that does pass through consists of dynamic requests requiring active processing. To mitigate DDoS attacks, these incoming requests must clear a web application firewall. Once sanitized, this remaining dynamic traffic is funneled into a central API gateway. This diagram maps the perimeter flow. The API gateway processes OAuth2 and JSON Web Token authentication, isolating all security protocols entirely outside the core application logic. The perimeter layer functions as a system of aggressive deflection. It ensures the compute engines expend resources exclusively on legitimate dynamic tasks. With the perimeter secured, the next challenge is processing the authenticated traffic during violent, unpredictable spikes in user volume. This requires abandoning the monolithic model in favor of modular microservices, where discrete application functions operate as entirely separate processing entities. For this modularity to work, the microservices must be completely stateless. They cannot store any local user session data on their specific server instance. Without localized data tying users to specific servers, the system can duplicate instantaneously to meet rising demand. This is managed by Kubernetes horizontal pod autoscaling, which shrinks and multiplies identical stateless containers to match fluctuating traffic. The HPA continuously monitors real-time CPU and memory metrics, triggering instant container deployments across distributed multi-cloud environments. This horizontal elasticity provides immediate capacity, bypassing the slow downtime and high financial cost associated with manually upgrading hardware. By removing persistent memory from the compute layer, the system clones its processing power exactly when needed to neutralize surges in traffic. Even with elastic compute power, a downstream bottleneck remains, surviving the load of 100,000 simultaneous requests attempting to write data to the database at once. If the database writes are synchronous, the fast microservice must sit idle, waiting for the slower database to confirm the data is saved. Looking at this flow, that idle time triggers a chain reaction. Processing delays compound rapidly, instantly pushing response times well over our 200 millisecond ceiling. The architectural solution is to insert a shock absorber, a message queue, utilizing a tool like Kafka or RabbitMQ. Here, we implement asynchronous messaging. Instead of connecting directly to the database, microservices deposit their data into the queue. The microservice drops its payload, immediately registers a successful response to the user, and moves to the next task without waiting on the database. The database then pulls tasks from the queues sequentially, operating at its maximum safe speed without ever risking an overload from sudden spikes. Severing the direct dependency between fast compute components and slower storage components resolves the conflict between high throughput and low latency. At the final resting place of the data payload, a singular database remains a fatal point of failure. The specification requires multi-region disaster recovery to uphold the 99.99% uptime guarantee. This chart illustrates database charting. Using tools like Cassandra or CockroachDB, the system splits the total dataset into smaller segments and distributes those pieces across multiple geographic zones. Distributing data prevents any single storage instance from becoming too large, enabling horizontal growth without degrading performance. If a regional database collapses, failover mechanics automatically detect the outage. Traffic instantly reroutes to a synchronized replica, preserving data integrity and uptime. Managing this distributed complexity introduces a strict maintainability requirement. Human engineers cannot manually monitor millions of discrete server actions per minute. Total systemic observability is an infrastructural component, equal in operational importance to the compute engines themselves. The system relies on the ELK stack, Elasticsearch, Logstash, and Kibana, to aggressively aggregate and structure massive volumes of server log data. Simultaneously, Prometheus gathers real-time cluster health metrics on Grafana dashboards. This data continuously feeds back into the Kubernetes HPA to drive precise, automatic scaling decisions. At this scale, observability functions as an automated nervous system, actively adjusting resources to keep the architecture alive. This is our final interconnected architecture. A single user action using WebSockets travels from the user, clears the CDN and WAF, passes authentication at the gateway, is processed by a stateless microservice, drops into the Kafka queue, and secures itself in a sharded database. Extreme processing volume is handled exclusively through disciplined decoupling and broad geographic distribution. Because the blueprint is strictly modular, future enhancements such as injecting serverless functions to handle extreme edge case traffic bursts integrate seamlessly into the existing flow. This living blueprint relies entirely on rigid, interlocking systems executing complex data logic without requiring any manual human intervention. Architecting a high-performance distributed system is an exercise in translation. It requires taking raw, abstract mathematical constraints and converting them into a resilient, living global infrastructure.